So let's have a look at the problem. Researchers claim that there's a difference in the average number of minutes that juniors in schools of public health and in schools of engineering and applied sciences exercise each day. So they claim that it is just different. Immediately we can see that, as far as this claim is concerned at least, there'll be a two-tailed alternative hypothesis. That's their claim. So they randomly select 61 students from schools of public health and 72 students from schools of engineering and applied sciences. Now the schools of public health students, they exercise on average 31 minutes per day. So there's the finding from the data that they collected, with a standard deviation of 4 minutes. And the students from the schools of engineering and applied sciences, they exercise on average 29 minutes per day with a standard deviation of 5 minutes. And we need to test their claim at the 5% level of significance. And so here we go. I've already started the problem by writing down the summary of what we know. So I've decided that I'll make group 1 my schools of public health students. Group 2 will be the students from schools of engineering and applied sciences. So that's my choice. What I do recognize here is that this minutes exercise per day, the level of measurement of that variable would be ratio type. I mean, there's a true zero, in as much as if you exercise 0 minutes a day, that's the absence of any kind of exercise. And so that's great, because from that we can calculate means and standard deviations. But we also need another variable, which is binary. It's categorical and of nominal level of measurement, and there's only got to be 2 outcomes. And this would be so for these students. A student can either only be from the School of Public Health or the School of Engineering and Applied Sciences. So as soon as I see that, I know that a t-test might be appropriate. And we see there, we've used, as I said, group 1 and group 2. We see the number of subjects in each group. We see the 2 sample means. We see the 2 standard deviations. And we know that we're going to use variance as well. So we're going to calculate the variance that wasn't given in the problem. You have to do that. So 4 squared is 16 and 5 squared is 25. So the variance in group 1 is 16 squared minutes, and the variance in group 2 is 25 squared minutes, whatever a squared minute might be. Remember step 1, what's the whole aim here? The whole aim here is to understand what these values might be in the population. So mu sub 1, that's the average number of minutes that students in schools of public health, I put a little superscript S there, it says that's the whole population. Students in schools of public health exercise daily, and mu sub 2, that is the mean or the average number of minutes that students in schools of engineering and applied sciences exercise daily. And that's definitely what we want to know. So let's write down our hypotheses, and under the null hypothesis, we're going to have that mu sub 1 minus mu sub 2, the difference in the population and the average number of minutes that these two groups of students, populations of students exercise, is going to be 0. And we read there that the claim is that they are not the same. And so it's going to be a two-tailed alternative hypothesis. So mu sub 1 minus mu sub 2 is going to be not equal to 0. We know that we can do simple algebra here. And so what we really mean is that mu sub 1 equals mu sub 2, simple algebra, and mu sub 1 is not equal to mu sub 2. But that's not how we write it. This is how we write it. This is the way that we think about it. So let's do step number 3. And that is just to write the level of significance. And we were told to use a 5% level of significance, so alpha is going to be 0.05. Let's think about step number 4. Let's think about step number 4. So we have to think about the test that we're going to use, and we've already discussed that. This is going to be a t-test. We have a random variable, and its level of measurement is ratio type numerical, and so we know that we can calculate means and standard deviations and variances. And we have another variable which is binary, and if you think about, if you were to write this in a spreadsheet, there'll be a spreadsheet on one column that'll just have all the minutes exercise per day, and the second column will be what group that specific subject is in. Is that subject in the School of Public Health or the School of Engineering and Applied Sciences? And so we know that we're going to do a t-test. Let's write that down. We're going to do a t-test. We don't know what t-test we're going to do because there are equal and unequal variance t-tests. So we better have a look at which one. Now we always discuss there are statistical tests for this, such as Levene's test. The null hypothesis of Levene's test would be that these variances are equal and the alternative hypothesis they're not equal, but we're just going to use the ratio of variances. And I'm going to write that in green because that's a formula we want to remember. So it's going to be S1 squared divided by S2 squared. And the whole idea here is, with this very rule of thumb, is that we don't want one to be more than twice the other. We don't want one variance to be more than twice the other. So that was arbitrary which one was group 1 and 2. So this division, what is in the numerator and denominator, is also arbitrary. So we set that it's either 1/2 or twice. And so if we do this, that's going to be our interval. Our variance was 16 squared minutes divided by 25 squared minutes. And that equals 0.64. And that's definitely within this interval of ours of, as I say, 1/2 to 2. We don't want one to be half of the other or one to be more than twice the other. If it's on that interval, we're going to use the equal variance t-test. Equal variance. And that's exactly what we're going to do here. Equal variance t-test. Now, the assumptions for this test, we have to have IID. And that is the fact that all our subjects here are independent of each other. We're going to assume that that is so. And that each observation is from the identical distribution. And we're going to assume that as well. Furthermore, our sample sizes are big enough, so we're going to say that we can use the central limit theorem. So we're going to accept all of these things. We're already accepting the fact that this is a numerical variable and all the things that go together with using the t-test. What we want to know, though, is just the degrees of freedom. Now, we've decided an equal variance t-test, so let's just here in step number 4, just do all of these things. When it comes to degrees of freedom for the equal variance t-test, nu is going to be n sub 1 plus n sub 2 minus 2. So that's going to be an easy one. So we have 61. Nu for us is going to be 61 plus 72, that's 133, minus 2, that's going to be 131. So we know we're going to use a t-distribution on 131 degrees of freedom. That's going to absolutely determine what our probability density function, or at least the graph of that, would look like. So let's go to step number 5. So we're going to say our test statistic, that's definitely going to be a t-statistic. It's going to be described by the t-distribution, and in this case, as we said, on 131 degrees of freedom under the null hypothesis, under h sub 0. Okay, so I've gone ahead and actually, just made these two little circles, and I want you to imagine the following, just so that we understand what does this all mean, just as a little revision. I'm imagining that this is the population of all students in schools of public health. This is a population of all students in schools of engineering and applied sciences. And what I'm going to do is I'm going to select 61 students at random from this population. I'm going to take 72 students at random from this, and I'm going to assume, under the null hypothesis, I'm going to assume that these two populations have exactly the same mean, population mean, for this random variable x, and x is the number of minutes that these students exercise every day. Imagine that is so, that these two are exactly the same. I'm going to randomly select 61 subjects, 72 subjects, and I'm going to calculate a t-statistic. And we will see, we'll remind ourselves of what that formula would be. And I might do that today. Tomorrow I go and I randomly select, and again, just a total random, 61 students and 72 students. I have my calculation, I calculate a t, I've got a second t, I've got a third t, but that's under the assumption that these two means are exactly the same. And then that means I'll get a distribution of these t-values. On some intervals, it'll be very common to find t-values. On some intervals, I won't find many t-values, but that's going to be all the t's that I find. If I draw my probability density curve, all these t-values are all possible given that this situation is true. I'm assuming that this is true. Then I'm going to get, if I were to do this an infinite number of times over and over again, I'm going to get a distribution of t-values. And we're saying, theoretically, that the distribution of these t-values can be described by this t-distribution on 131 degrees of freedom. Now, of course, that 131 would be calculated differently if this was an unequal variance t-test. But even then, we're going to have a degrees of freedom, and we're going to say then that that t-distribution, under those assumptions of these two being the same, but the variances not being the same, if that was true for these two populations, I'm going to get a slightly different distribution of t-values under 8 different degrees of freedom. And that's what we calculate if we use an unequal or an equal variance t-test. So I hope that's a good reminder of what we mean by this statement. We're assuming that these populations are the same in this instance, that not only are the these two means the same, but the variance is also the same across the two, and I'm just over and over and over randomly selecting these two number of subjects, and I get all these t-values, and they'll form some pattern of t-values. So let's remind ourselves of t. We're going to say the t-statistic, well, we take the mean of group number 1 minus the mean of group number 2, and we have to subtract from that mu sub 1 minus mu sub 2, because it's not always 0. There are reasons in some research why we don't set that to equal to 0, but under our null hypothesis, this is 0. So that would just simply cancel out. And so let's divide that by some standard error. And it's always the difference in the statistic expressed in units of standard error. That's how we do all of these statistics. Now we just have to remember how to calculate the standard error for the equal variance t-test, and for that we need the pooled variance, s subscript p squared. And that's going to equal n sub 1 minus 1 times the variance for that group plus n sub 2 minus 1 times the variance of that group. And we're going to divide that by adding these two sample sizes, n sub 1 plus n sub 2, and we subtract 2. And that allows us to calculate the standard error, which is going to be the square root of this pooled variance divided by n sub 1 plus the pooled variance divided by n sub 2. So we need all of this in our calculations. I put that in green. I always like to put all my formulas and definitions in green so that they stand out. So let's calculate this. So let's start with sp squared, this pooled variance. Now n sub 1, we just have to remember what n sub 1 was for us. That was 61 minus 1, and the variance there was 16, plus we had 72 subjects there, minus 1, we're going to multiply that by 25, and then we had divide by 131. Remember, 61 plus 72 minus 2, well, that is going to give us 131. And let's try and keep it neat. Now you've got to use your calculator for that. I think that comes out to about 20, let's make it 20.87786, which means we can calculate the standard error. I'm not going to write all of that out. Please check that. I'm going to do this divided by 61 plus this divided by 72. Add those two, take the square root of that. Please check on that. I think it's about 0.7955129. Now it's going to depend, where you start doing all your rounding, and so you might get a slightly different value. So that means we can now calculate a t-statistic, and that's going to be the difference of those two means we had. That was 31 minus 29. Remember, minus the 0 for under our null hypothesis, that was going to be 0. And we're going to divide this by 0.795129, and check on your own calculator. You should get a t-statistic of about 2.515. And that's great. We've calculated that now, and that's nice. It brings us now to our step number 5. And our step number 5 is, step number 6, I should say, apologies for that. And that is now going to be our decision rules. And so we need a critical value, t-crit. Now, this is going to be based on our degrees of freedom and our level of significance. We want those two intervals on our PDF that would be the least probable t-values. So you've got to use software or calculator for that. Please check on that with the calculator that we use. I get 1.978, and there we go. Now this is a two-tailed alternative hypothesis. So when we use the critical value approach, we are going to reject the null hypothesis if the absolute value of our t-statistic is more than the absolute value of our critical value, and that is positive, negative 1.978. I've got to do both sides of my PDF, and in this instance it is true. 2.5 is larger than that, so we're going to reject the null hypothesis, and we're going to accept the alternative hypothesis. There we go, we accept the alternative hypothesis. We can also have a p-value approach. So once again, you can use the calculator or software to calculate the p-value for this t-statistic. And if you do that, you should get about 0.013. And we have that p is less than alpha. And once again, we're going to reject our null hypothesis, and we're going to accept our alternative hypothesis. So I'm just going to draw this. So I'm going to say this is definitely not the t-distribution, the graph of the PDF of that, so just forgive me for that. So this is our t-distribution on 131 degrees of freedom. And we're saying, remember, this is all the possible t values that I can get given null is true. So all the values of t here are completely valid values under the null hypothesis. We're just going to say, well, arbitrarily, let's just choose these regions, these intervals, where I would find the least probable 5% of these t values. And that's going to be my critical values, and we found the critical value of negative 1.978 and 1.978. If I'm so many standard errors away from 0, if I'm that far or more extreme or further away, I would get 2.5% of the least probable t values under the null hypothesis. And if I go negative 1.978 standard errors or more away from 0, this is where I would find the other 2.5% least probable values. And now look at what we found. We found a t value of 2.515, and so that's going to be somewhere out here, right out there. So I'm just trying to extend here a little bit because I want to show you what I mean by that. This is what we find. So what is the probability of finding what we found or more extreme? So that's going to be all this area under the curve, and we've got to do the same at negative 2.5, all of that area under the curve. If we use software to calculate this, remember that's the probability of t landing in these two regions, from there more extreme, from there more extreme. Remember, this is 2.515, that's what we're trying to say. This one's negative 2.515. A value in this region or more extreme, those little areas under the curve, that's 0.013 of the area under the curve. So I've written a test conclusion there. There's enough evidence in the data at the 5% level of significance to show that the average number of minutes that students in schools of public health and schools of engineering and applied sciences, so look at that, I'm talking about the whole population, exercise per day is not the same. Now, if I failed to reject the null hypothesis, I would stop there. But because we have shown that the claim is now true, we'd go ahead and say, in fact, students in schools of public health exercise on average 2 more minutes per day. The difference there between 31 and 29 minutes, that's 2 minutes. So on average, 2 minutes per day.